3.9 differentials. Linear approximations. Write the equation of the tangent line at c, f of c, for a function of f that is differentiable at c. So if you're writing a tangent line, you can use the point-slope form. And the point-slope form is y minus y1 equals m times x minus x1. Or it's the same thing as y minus f of c equals f prime of c, because it's the slope, times x minus c. You could also rearrange that so that you would have y equals f prime of c times x minus c plus f of c. It's all the same thing, it's just their equivalents. The equation of the tangent line can be used to find a local linear approximation close to C. Example 1. Find the equation of the tangent line t to the graph of f of x. Square root equals square root of x at 1, 1. Use this linear approximation to complete the table. So what you would need, since you already have your points, so you have your c and your f of c, all you have to do is find your slope at that point, so you find the derivative of f of x. So f prime of x equals to be 1/2 times x to the negative 1/2. So it's 1 over 2 root x. And after that you just plug in your x point, which is 1. So 1 over 2 root 1, and that just equals to be 1/2. So your tangent line is y minus 1 equals the slope 1/2 times x minus 1. So for the table, for your linear approximation, all you have to do is plug in your x value into the equation you got. For this one, it's f of x, so it's the square root of x. That is, comes out to be 0.94868, and it goes on. If you plug in t of x, 0.9 to t of x, you end up getting 19 over 20. Or 0.95 if you plug it into the calculator. And you just keep doing it for the rest of the other points. So for 0.99 you get 0.994987. So remember, this is when f of x is this equation, so you plug that into square root of x. T of x is the equation we got earlier, which is really y equals 1/2 x minus 1 minus 1. Or if you want to simplify it further, it's 1/2 x plus 1/2. So that's t of x. And then so for when you plug in 0.99 to t of x, you get 199 over 200, or 0.995. If you plug in square root of 1 into f of x, square root of 1 is still 1. And then if you plug that in for t of x, 1/2 plus 1/2 is 1. Plug in 1.01 for f of x is 1.004987. And then if you plug it in for t of x, it's 1.005. Same thing for 1.1. It's 1.048888. And then for t of x, it's 1.05. So they're really close. And for the next part, differentials. Let y equals if f of x represent a function that is differentiable in an open interval containing x. The differential of x, denoted dx, is at any non-zero real number. The differential of y denoted to dy is dy equals f prime of x dx. So the change in y equals f of c plus delta x minus f of c equals to the f prime of c delta x. So example number 2, use the information to evaluate and compare dy and delta y. So for dy, if it's y prime, this equals to be 6x. And remember, y prime is dy dx. So if you just multiply dx on both sides, you have your dy is 6x dx. They gave you your x and they gave you your dx. And you just plug that in. And you get 1.2 for your dy. Now if you do delta y, which is this equation, delta y equals f of c plus delta x minus f of c. You would get 3 times 2 plus 0.1 squared, because your x is x squared, minus 5 minus f of c, which is f of 2, which equals to the 2 squared 4 times 12 minus 5 equals to be 7, so minus 7. And then if you add this together and square it, you get 3 times 4.41 minus 5 minus 7, and that equals to be 1.23. So as you can see, they're really close to each other. It's just off by 0.03 if you use delta y instead of dy. Error propagation. F of x plus delta x minus f of x equals delta y. So the inside is the exact value, delta x is the error, f of x is the measured value, and delta y is the propagated error. And it ends up being f prime of x delta x. So for example 3, suppose that the side of a square is measured with a ruler to be 10 inches with a measurement error at most plus or minus 1 over 32 inches. Estimate the error of in the computed area of the square. So you have a square which has x. So you're looking for the area, so your area would be x squared because it's length times width. And if you find a derivative of that, you get 2x. Each side is 10 inches, so x equals 10 inches. Delta x is, it told you that it changes, or there's an error, measurement error of plus or minus 1 over 32 inches. So if we use the delta y equals f prime of x delta x equation, you get 2x because it's your f prime of x, and your delta x times delta x. So you just plug in your x and your delta x that you found. So it's 2 times 10 times plus or minus 1 over 32. And then you end up with plus or minus 20 over 32 inches squared because it's area. if you simplify that, it's 5 over 8. So there's a negative 5/8, and there's a positive 5/8, and dy ends up being somewhere in the middle of that. So dy equals plus or minus 5/8 inches squared. That's the change in y that you found. So if your function is y equals x cubed, the derivative is dx equals 3x squared, and your differential is dy equals 3x squared dx. Example 4, find the differential dy of the given functions. For a, it's y equals x cosine x. So if you derive the first, you derive both sides. So if you derive y, it's dy dx equals, and then derivative of x is 1 times cosine of x plus derivative of cosine of x minus negative sine x times x. That's the derivative, and if you want to isolate your y because you're looking for dy, so all it is cosine x minus x sine x times dx. So you want to do the same thing for the second one, for part b. Y equals 1 plus 2x to the negative 17th power. You derive it. Negative 17, 1 plus 2x, negative 18 times the inside, which is 2. So that equals to be negative 7, negative 34, 17 times 2. 1 plus 2x to the negative 18 power, and you multiply dx on both sides. So you get dy. You could also put this on the bottom because it's negative 18, so if you put it on the bottom, it's positive. So dy equals negative 34 over 1 plus 2x to the 18th power dx. So on part B. So for part part D, there's no part C. Y equals 1 minus x cubed over 2 minus x. You do the same thing you did for the ones before. So dy dx equals to the derivative of the first times the second minus the derivative of the second times the first all over second squared. Multiply dx on both sides. So dy equals negative 3x squared times 2 minus x minus negative 1 times 1 minus x cubed all over 2 minus x squared dx. So now you could just simplify this stuff, combine, add, distribute. So you have negative 6x squared minus or plus 3x cubed. So that's plus 1 minus x cubed all over 2 minus x squared dx. And then combine it some more exponents. So it's negative 6x squared plus 2x cubed plus 1 all over 2 minus x squared dx. And then for exercise 5, the function f is twice differentiable with f of 2 equals 1, f prime of 2 equals 4, and f double prime of 2 equals 3. What is the tangent line approximation? Is the estimate greater or less than the true value? So you want to find the tangent line first, tangent line approximation. So you have your points for 1 and 2. So y minus y1, which is 2, equals your slope at 2, which is 4, times x minus the x you had. So your x is 2 and your y is 1, so 2 comma 1. So y minus 1 equals slope of 4, x minus 2. Just isolate the y, 4 times x minus 2 plus 1. Plug in your x that you want to approximate, which is 1.9. You get 1 plus 4 times negative 0.1, and you get 0.6. Now you have to figure out if your estimation is greater than or less than your true value. If you look at the second derivative they gave you, it's f double prime of 2 equals 3. Since it's positive, f double prime of 2 is greater than 0, it means that f of 2 is concaved up. So your approximation is less than your actual value. Alright, for the next part, we're doing a practice AP question. So, the volume of a spherical hot air balloon expands as the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of a balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes, for time interval of 0 to 12. The graph of r is concave down. The table above gives selected values of the rate of change r prime of t of the radius of the balloon over the time interval 0 to 12. The radius of the balloon is 30 feet when t equals 5. Estimate the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give a reason for your answer. So it tells us that the balloon, the radius is 30 feet when time equals 5. So it's 530. So technically you have your x and your y there. So remember you used the point slope form, y minus y1 equals mx minus x1. So we have so far y minus 30 equals, and then we're given the rate at time 5 up here at the table. So you could just take that. So our slope is 2 times x minus our x1 is 5. And so our tangent line approximation equation is 2 times x minus 5 plus 30 and all you have to do is plug in the time that you want to approximate for. So we're trying to approximate for 5.4. So y equals 2 times 5.4 minus 5 plus 30. And that equals to be 2 times 0.4 plus 30. That equals to be 30 plus 0.8. And it equals to be 30.8 feet. So that's our approximation for time 5.4. Now it wants to know if the estimate is greater than or less than. Our estimate is greater than because it says that r is concave down. So if we're doing a tangent line, so obviously ours is above and greater than the actual value. Alright, so R1. You want to build a road from a cabin, a highway so that you can drive to the city in the shortest amount of time. The distance from your cabin to the highway is 4 miles and the city is located 9 miles down the highway. Where should you join the road to the highway if the speed limit is 20 miles per hour on the road and 55 miles per hour on the highway? The first thing you want to do is draw a picture. So for R1, you want to build a road from a cabin, a highway, so that you can drive to the city in the shortest amount of time. The distance from the cabin to the highway is 4 miles. So cabin to the highway is 4 miles. And 9 miles down the highway is the city. So we want to know which way is the shortest amount of time. You can find this work for using the Pythagorean theorem, and you end up getting x squared plus 16. So if you go down this road, it's 20 miles per hour. And if you go down this road, it's 55 miles per hour. If you check your endpoints and critical points, you should be able to find which ones will take the shortest amount of time. So you have 0, you have 9, and then you have to find a critical point using t of x equals the square root of x squared plus 16 over 20 plus 9 minus x over 55, because you're still driving on the dirt road and on this side you're on the highway. This is the other way you could take other than this way, or straight up going across. So you want to derive that, find when it equals to 0. That's at approximately 1.561. So that's your critical point. And if you put it on the number line, and you plug it into your equation, you'll find that anything less is negative and anything higher is positive. Since t prime of x changes from a negative to a positive, it shows that it is a minimum. You should also plug in your endpoints and critical points to the original equation to check if they are the lowest. So if you plug in 0, you get 4 over 20 plus 9 over 55, which equals to be 20 over 55. Or 4 over 11, which is about 0.364 hours. Same thing with 9, which is the square root of 97 over 20, and it's about 0.49 hours, 492 hours. And if you plug in 1.561, you would get 0.350 hours. And if you compare them, you can see that this is the lowest amount of time, showing that it's the minimum.